Coming down, this is our rain collection system, and the cistern back here is already full of water. So we'll turn it on. And so now the ultrasonic sensor is sensing how much rain is in the cistern, and it's pumping it off to the water tower. Now we'll give it the sun. This will have to warm up a little bit. While that's warming up, I'm going to pull the plug out of the drain in here so that you can see the operation of the level sensor. And you can see that our vents are closed because the temperature is below the 70-degree mark. The vents shall open up once the temperature reaches approximately 78 degrees. And that won't take very long. We're at 69 right now in the greenhouse and 65 in the living room temperature. So you can see the water from the water tower is being gravity fed into the plants. And if I take the drain here and I plug it to where this water is going to start to come up a little bit, and once it reaches to the desired level of moisture, it shuts off the ball valve and doesn't give it any more water. We drain a little bit. Theoretically, the plants are using or transpiring, and it needs more water. It'll automatically turn on and water the plants flawlessly. And now our temperature is at 72, and the living room temperature is at 66. And you can see how this wall that we framed in really makes a good barrier in between the light coming in and the heat of the greenhouse and the comfort that you would get in the living room of the structure. It really works well. Even though it's not insulated, it still works really well. It's just a model. But you can imagine at a full-scale house that this thing would work even better. Alright, we're at 76 degrees right now. We're at 67 in the living room. Still really nice. And as soon as this hits approximately 78 degrees, both of these vents will open up, and that will begin the convection process. And you can see the cold air tubes in the back. What's going to happen is when these vents open, it's going to be pulling cold air from the tubes in the back. And that cold air is going to be coming into the greenhouse, and it's going to be letting all the heat come up through the top and escape out the top and start to bring the temperature back. In a real-life scale model, you would be able to shade this. Obviously, it would be filled with a lot more plants. Theoretically, this is a 33-foot greenhouse. So you could have trees in here, banana trees, avocado trees. It's a lot bigger than normal greenhouses and earthships. So we're at 79. You should see these open at any time now. Oh, we have a couple more degrees to go, that's right. So, yeah, you will have a lot more growing room in this design than a regular earthship. I can't believe that they make those greenhouses so small in the real earthships that they have in Taos. It should actually be able to take care of all your needs as far as food goes and growing food. You should be able to grow everything you need in here. And any second now.
So I've got a question. What is that material on the back wall there?
So the material on the back wall is all clay. It's clay in the back, it's clay in the front, it's clay on the sides, and then it's just silicone on there, and then it's just some caulking for the cracks. As it settled, it cracked. And,
okay.
And there we go. The vents open up.
Hey, look at that.
And so we'll kill the sun. And that is the shred.
Nice. Nicely done.
Any questions?
I've got a question. So, you've got plants in the front here.
Yep.
You said that, I don't know, you probably have the set point set for demonstration or whatever, but you want the greenhouse to be warm, right? Typically warmer than your home is gonna be for comfort and all that, so, have you thought about ways that you could make that system heat up more quickly, more efficiently? I'll give you a hint, it's something I asked you about the material for the back wall.
Go ahead, or do you got it?
No, go ahead.
Okay, so for this model, normally the back would be a darker shade
Ah, there you go.
because darker shades absorb heat better than lighter shades. This model, you could say, is designed for the desert, where you wouldn't want that extra heat in the back, and you'd want it to be reflective. But you're exactly correct. You would want a darker shade in the back, and that's typically how most Earth ships are made. And the biggest thing about Earth ships and how they stay warm is thermal mass. Thermal mass is the key to this whole deal. When the heat comes in, it heats up that thermal mass. When the sun goes down, that heat from that thermal mass is going to be released slowly throughout the night until the next morning.
So, next question then, same area, this is from Mark, you did a lot of the research for this project?
That's correct.
Is that just a piece of plexiglass in front there, what is that?
That's correct. We use plexiglass for all of our clear needs, and in a normal greenhouse we would probably use a different material. But for this we use plexiglass. It worked really well.
So let me ask you a question. So if you had a version 2.0 and you had, let's say, a budget that was, that you could do what you wanted with, is there a different material that you would use for that front glass? And I asked that kind of in reference to Matt's point about, the sun comes up, it heats up, okay, this is designed for the desert, fine, you make the back wall white. What about at night when heat is radiating out?
We would want to use probably double pane or triple pane glass for that to help insulate that greenhouse, because at night it is going to cool off.
Did when you researched stuff, did any of your research cover any coatings for the glass?
We did not actually. We just looked at the plexiglass.
Coatings can do amazing things on glass, right?
Yeah.
How heat is transferred from, the thermodynamics of how that works, how heat goes in, how heat's going to come out, and all that. So, something we're looking at that version 2.
Absolutely.
Solar glazing.
Anybody else?
Yeah, I got a question for you.
Yes, sir.
Let's start with it there. How many sensors are you using in this, and what type of outputs do they have?
We're using 4 sensors, sir. And we're using two DHT11s, 1 Dallas, and then 1 sensor, sir.
Okay,
One,
what type of
water
outputs
level.
do they give you?
I'm sorry?
What type of outputs do they give you?
Tap out digital.
Okay. Let's go with John.
Sure,
Got a question for you.
absolutely,
All right, you got this nice, wonderful water tower up there.
absolutely.
Let's say we get some unseasonable rains and we get a lot of it. Do you have a way to stop that from being overfilled?
So the top is obviously, it's not gonna be empty. Are you talking about when the cistern gets too hot? Is that what you mean?
I mean, you've had way too much rain.
Okay, so you had too much rain, the cistern got too full, the water tower is excessively full. I think that at that point, it would just overflow. I'm not exactly sure, we didn't think about a process in terms of excessive water usage. Definitely, we looked at more of a desert climate, I think, and didn't look more in terms of what would happen if we did get too much rain. That is something we should look at, though, I agree.
All right, what about too little rain?
So
You
too
say
little
your
rain,
cistern maintains a certain level,
correct.
but you need water in your tower to be able to feed your plants.
We do. So we didn't think about that either in terms of what we would do if we didn't get any rain. We used the simulated rain here just to be able to show you what would happen. I think in general you probably would have to find some external source of water, depending on what that might be. Sorry,
A well.
a well possibly, something along those lines.
That's it.
did you choose a sonic sensor device, a typical float valve for your water level sensing?
Are you asking me?
Yeah.
The reason we chose an ultrasonic sensor for our cistern over a float is because the float valve itself is a mechanical device. And being in an environment where you have a lot of moisture, we didn't want the float to rust, because if it rusts, you're gonna lose that mechanical ability to go up and down. With the ultrasonic sensor, you don't have to worry about things like rust, and especially in the wintertime, you wouldn't have to worry about the ultrasonic sensor freezing in place, like you would get condensation on a float pump mechanically, and the gears would freeze and it wouldn't work anymore. So the ultrasonic sensor was the top choice.
Okay. Mark, for you, I'm glad you brought that up because that leads into my next question. What do you do in the winter in the desert when the temperature drops below freezing and you have that possibility, or the possibility of having the water in your tanks freeze? Have you thought about how you mitigate that?
So ideally, in a situation where you have really cold temperatures, we would actually have the cistern would probably be included in the structure of the house. That way, so as the water flows down, either snow melt or something like that into the gutters, the cistern would actually be inside the structure itself, and would probably be underground in order to keep it at a kind of a medium temperature. The water tower itself, we would have to come up with a different idea for that in cold temperatures, possibly also within the structure.
Now, what are you using to pump your water to your water tank? How are you moving that water
To the tower itself?
Yeah, to your tower. And the reason I'm asking this is because, based on the fact you said that is approximately 30 feet tall, is that correct, Matt?
Correct. Up to here is 33 feet, and up to here would probably be about 40, so you're looking at a 60-foot water tower.
Okay, so we're looking at a 60-foot water tower. Have you thought about the amount of pressure that is going to be required to pump water that high?
Yes, and I imagine the motor would be to scale as well.
An AC motor, a DC motor, what are you looking at?
We're looking at an AC motor, or, well, for this, we could have an inverter and have an AC motor. We could use a DC motor, but that's going to have a lot of current draw for a battery system, and I don't think that you'd want to have that type of current draw on your entire system. So it would probably have to be an AC motor on its own battery, really, to be able to pump water that high. But the other alternative would be that instead of having a water tower, as we have for this type of demonstration, out there you would probably just have your tower uphill, so you'd be pumping it at a lower grade. It wouldn't be a vertical feed. It would be a gradual pump uphill to a tank, to a tower, and then back down the hill for your gravity feed would be the natural way to do it in reality. For demonstration, this was the way that we had planned to get our gravity feed.
Unfortunately, it doesn't matter how gradual it is, it's elevation that counts here. So even if you're pumping at a 1 degree angle, you're still taking it up that high, you're still dealing with, pressure that you have to overcome.
Well, as long as you have the pump close to the source, you're going to get a lot more pressure from the pump, pumping it uphill that way. I've personally pumped fluid a very long way with a pneumatic chugger pump, but the trick to it was that you had to have the chugger close to the source of what you're pumping out, instead of having it close to the tower that you're trying to pump to and from. I mean, pumps can generate an immense amount of power, and depending on the size of the tube, you can increase or decrease your pressure if you're pumping it uphill.
And I have just 2 comments, not questions. First, at the very introduction of the slide presentation, you gave us no idea what SHRED stood for. You should always tell us what it is and then give us the acronym afterwards.
Yeah, I forgot about that.
So I didn't know what it was until we got to the very end. And the other thing is, Mark, I'm going to pick on you, buddy. I'll be honest, I marked you down on your appearance because you're the only one without a tie. Okay. Otherwise, I think you look great, you look very professional. It was an outstanding, in my opinion, outstanding presentation.
My turn. So I'm going to ask the same question of all 4 of you. before we close out, so. What was the one biggest takeaway you took from this trip?
Teamwork. Too many chiefs, not enough Indians. And you gotta learn your place. That was my big thing.
I would say bringing it all together was one of the biggest things that I learned. Just being able to work on all these things separately and then come together at the end and get it all working and have it all set up in one big process. It was a giant stepping stone for us. I think we had all these big ideas, like you were saying, and to be able to finally get the knowledge to put it all together and to know that we could go do this again with something else if we wanted to is an incredible feeling.
I think setting goals and meeting our timelines for the project was really great. Like we said, we had so many goals and things that we wanted to get done, and we got them. We got them all done. And it was amazing to see that we actually had time to spare towards the end because we worked on it every week, and it was a great feeling to get that done with the guys.
What I took away from this and lessons learned is that I really did receive a good education at Ecotech. I'm able to do everything that I wanted to be able to do when I started this school, and this proves it. We all got together on this, and we were told from the very beginning that this was an impossible accomplishment and that people would really be surprised if we could pull this off. We did pull it off, and I'm really happy with that. And what I learned is that when you really want to get something done, it can get done in a timely manner, on time, and with perfection.
Great presentation, guys.
Well, that's a nice Christmas present to me, to hear. That's great, you guys did a great job with this. I've got one final